We use it literally every second of every day, right? But how does it actually work? I'm talking about the internet. Today, we're going to follow the insane, high-speed journey your data takes from just a simple click to a web page loading in, well, an instant. Let's dive in. It's something we totally take for granted. You click a link and boom, almost instantly, a web page from halfway across the globe just appears. It feels like magic, right? But it's not. It's this brilliant, super fast, step-by-step process. So what is really going on in those few milliseconds? All right, so let's start at the very beginning. That click, it's not just a click. It's the starting gun. It's what kicks off this wild global relay race, a chain of events that zips across the entire planet in literally the blink of an eye. So that little tap on your phone or that click of your mouse, your browser translates that into a really specific command. It's basically shouting out to the network, hey, go get me the information at this address. And just like that, your request is officially on its way. Okay, but for your browser to even ask for that data, it's got to speak a language the server can understand. And that language, it's called HTTP, Hypertext Transfer Protocol. Your browser wraps up its command into what we call an HTTP GET request. This is all happening at the very top layer of the internet's architecture, the application layer. That's the part we, actually see and interact with. All right, so your browser has its request ready to go. But where does it send it? I mean, the internet is a network with billions of devices. We've got to find the one exact unique address for the server holding the web page you're looking for. And here's our first big hurdle. We humans, we're good with names, right? Like Google.com, easy to remember. But computers, nope. They think in numbers. Every single device on the internet has its own unique numerical label. That's its IP address. So the big question is, how do you translate the name we type in into the number the computer actually needs? Think of it this way. It's exactly like a mailing address. The host name, like gaia.cs.umass.edu, that's like the person's name. But the IP address, that long string of numbers, that's their actual street address, city, and zip code. You might remember your friend's name, but the postal service, they need the address to actually deliver the package. So this magic translation, it's handled by something called the Domain Name System, or DNS. And honestly, the best way to think about it is as the internet's giant distributed phone book. It's just a massive database that looks up the name you typed and instantly finds the right number. And thank goodness for it, because without DNS, we'd all have to memorize strings of numbers just to check our email. Can you even imagine that? And this whole process happens incredibly fast. First, your computer asks a nearby DNS server, kind of like asking a local directory. If that server doesn't know, it doesn't just give up. It goes and asks another server higher up the chain. And that one might ask another, and so on, until the correct IP address is found and sent all the way back to your browser. And boom, our request now has a destination address. Okay, quick recap. We have our message, the HTTP request, and we have the address, thanks to DNS. So what's next? Well, now we have to package that message up so it can survive its long and, honestly, kind of chaotic journey across the internet. So imagine you had to mail a 1,000-page book. You wouldn't just stuff it into one giant flimsy envelope, would you? Of course not. It would get lost or torn or just never make it. A smarter way would be to send it page by page, with each page numbered so the person on the other end could put it back together. Well, the internet does the exact same thing with your data. It's a brilliant technique called packet switching. And the protocol that's in charge of all this? That's TCP, the Transmission Control Protocol. Just think of TCP as a super organized, slightly obsessive shipping manager. Its job is to take your request, chop it up into smaller numbered pieces called packets, and then make absolutely sure they all arrive safely and get put back together in the correct order. This is the reliable manager in the internet's famous power couple, TCP/IP. Okay, so now we have all our numbered postcards, right? Each one now needs its own envelope. And every single envelope needs two critical pieces of information. The to address, that's the IP address we got from DNS, and a from address, which is your computer's IP address. That way the server knows exactly where to send the web page back. And this digital envelope, that's the IP part of TCP/IP, the Internet Protocol. Each of our little TCP segments gets wrapped up inside an IP header. And that header, you guessed it, contains the source and destination IP addresses. The fancy term for this is encapsulation, and it's a really core idea for how the internet is built in these neat, separate layers. And this is where you can really see how all the layers stack up. It's kind of like a set of nesting dolls. You've got your original message, the GET request, tucked inside the TCP segment, which is our numbered postcard, and that is tucked inside the IP packet, our mailing envelope. Each layer just adds the little bit of info it needs to do its job, and it doesn't have to worry about what the other layers are doing. It's just a beautifully elegant design. So our packet is addressed, it's packaged, it is ready to go. And now the really incredible part of the journey begins. A super high-speed global relay race across the actual physical wires and cables of the internet. The star players in this race are called routers, and you can totally think of them as the traffic cops of the internet. They're these specialized computers, and their one and only job is to grab a packet, look at the destination IP address, and in a split second, decide where to forward it next to get it one step or hop closer to its final stop. So a packet's journey is really just a series of these hops. It might go from your laptop to your Wi-Fi router, then out to your internet service provider's network. From there, it could literally jump onto these massive undersea fiber optic cables that form the internet's backbone, and then finally hop through a few more networks to land on the web server. And what's really wild is that all the other packets from your single request, they might all take completely different paths to get to the same place. And this right here, this perfectly captures the original vision of the internet's pioneers, guys like Vint Cerf and Robert Kahn. See, their goal was never to build one single giant network. The genius was to create a set of rules, protocols, that would let thousands of completely separate, independent networks all connect and talk to each other. They were building a network of networks. So, after zipping and hopping across the globe in just milliseconds, your packets all arrive. The server's own TCP shipping manager reassembles them in the right order, the application layer reads your HTTP request, and then it does the entire process in reverse. It packages up the web page you wanted into its own TCP/IP packets and sends them right back to your IP address. I mean, this whole thing sounds impossibly complex, right? But it works. It works billions of times a second, all around the world, with mind-boggling reliability. So let's take a step back and look at the simple, powerful ideas that make it all possible. So why does it all work so well? It really boils down to three simple but totally powerful ideas. First, that layered architecture we talked about, where you break a huge problem down into smaller, manageable pieces. Second, open standards. All the rules are published for free in documents called RFCs, so anyone can build a device that can talk on the internet. And finally, packet switching. That idea of breaking things up makes the network super efficient and incredibly resilient. And if you want proof that these principles work, just look at the growth. Back in the late 70s, the ARPANET, the internet's ancestor, had maybe 200 connected computers. Today, we're talking billions and billions of devices, all running on that same core foundation laid decades ago. It is, without a doubt, one of the most scalable and successful engineering projects in the history of humanity. So there you have it. From a simple click to a global journey and all the way back again. All of it orchestrated by a few elegant rules dreamed up in the 1970s. It really makes you think, doesn't it? As we're moving into this new era of AI and billions more connected devices, what are the simple, powerful rules that are going to define the internet for the next 50 years? Thanks for digging into this with me.